Hello, and welcome to episode 9 of the London Futurist podcast. There seems to be a paradox in AI. Research in the field is making great strides and indeed surprising practitioners. But the deployment of AI in industry seems slower than expected. In our last episode, Daniel Hume offered one explanation for this, which is that CTOs are understandably nervous about deploying systems that are unpredictable or allowing them to make mistakes without which they can't learn. To shed some light on at least part of this paradox, David and I are delighted to be joined today by Simon Thorpe. Simon has spent 40 years researching how the human brain works and what we can learn about that from computers. For much of that time, he's been a director at CNRS, the Centre National pour Recherche Scientifique, the National Centre for Scientific Research in France. He believes that AI is progressing much faster than almost anyone recognises, and that much more attention should therefore be paid to it. And he's got some particularly interesting ideas on why human brains, although much slower than computers, are so much more energy efficient than machines, and what we might do to change that. So Simon, welcome to the London Futurist podcast.
Thanks very much for the invitation.
And let me say welcome as well. And Simon, is there anything more you'd like to explain about your background as to what gives you your particular insights? I guess this is the tale of neurons and neurons, the neurons used in AI systems compared to the neurons in the brain.
Yes, so, well, I've been, as Callum said, actually it's 45 years now since I studied my thesis back in Oxford. And I've been trying to work out basically how the brain does amazing things like you flash up an image and 150 milliseconds later, are milliseconds okay? So, about a sixth of a second later, you get a signal being generated by the brain to say, oh, there was an animal in that picture, effectively. That was my big hit in 1996. We showed that the brain does this in a totally attention-free mode. You don't know what you're looking for. The brain just comes up with this answer, and actually that shook quite a lot of people in computer vision, because the old story was that we can't get our computer vision systems to recognise things because they don't know where they are. It would recognise a telephone if it knew it was in an office. But we showed essentially that it was all done what I think is in a feed-forward mode. In other words, the image comes in and it's just processed by a whole string of processing layers, and you get the answer out the other end. And that led me to think about how the brain does this, and basically throughout many of the ideas that people had been using, both in computer vision, but also in neural networks, where people thought that feedback was necessary. So you have all these processing layers with loops in them. You don't have time to do that. And so that's one of the reasons why I think human vision is a really interesting model for designing artificial systems. It was basically that I think led a lot of people to think, can we do this with a computer? And that's what led to the ImageNet challenge being solved in 2012 by Jeff Hinton and his two students. We basically thrashed the computer vision community with a really dumb feed-forward neural network. I should probably stop at this point.
Isn't some part of vision influenced by what we're expecting to see? Nevertheless, if you get somebody to look at the picture, they won't see it. But if you say, look, it's this, isn't it? They'll suddenly recognize it. It's the same with sound, isn't it? Some sounds can sound like one word or another word. Again, it depends on what we're prompted.
Yes, and people often think that, that's the secret. But actually, okay, let's take that case of there's this wonderful image that you see in psychology textbooks of a sort of Dalmatian dog, and it's just a pattern of dots, black and white dots. And when you look at it the first time, you can't make any sense of it. It just looks like just meaningless. And then somebody will say, oh, that's the head of the dog, and that's the tail. And you think, oh, yeah, there's a dog in there. Now, what is truly spectacular is that once you've done that once, it's for the rest of your life. And I've tried this, with my students. You sort of flash this thing up, and people will say, Oh, that's the thing that somebody showed me in a psychology course, like 20 years ago. So it sticks. So once you've learnt something, you don't need the context. I can flash up any one of hundreds of thousands, probably millions of different images, and you would recognize them instantaneously. You don't need to be cued to look for something. And indeed, one of the reasons why humans are so bad is that we tend to use that cueing thing. So if you're a security agent in an airport and you're looking for a pistol, and you're looking in the baggage and looking for a revolver or something, you might miss the hand grenade because you're looking for a specific thing. So actually, that's one of the reasons why I think airport security staff are going to be made out of a job extremely soon, because basically they're not reliable and they're messed up by having expectancies. You can get rid of those expectancies in artificial systems.
It's the same with the famous picture of the gorilla coming into a basketball court. If the viewers are asked, count how many passes are made, and then shockingly they fail to see the gorilla in plain sight.
Absolutely, that is one of the most impressive demonstrations of how bad humans are. Yes, we are completely distracted by things like doing a task, counting how many times the ball is passed, and you don't see the gorilla. It's just unbelievable. That you would never get that with an artificial system. So there are all sorts of situations like that where security people are hopeless because they will be thinking about something else or distracted by something. And the whole thing about conjuring tricks, it's all about attracting people's attention somewhere else while you're slipping something in over here. Humans are terrible.
So whilst we're singing the praises of what AI systems can do compared to humans, isn't it the case that humans use much less energy to do our calculations, and the AI systems are burning through huge amounts of wattage?
Absolutely, yes. So that, you might say, is one of the last things that you could say for a human. So if you take the standard model of how we think, most people think that an AI system based on neural networks works, it basically says you've got 86 billion neurons in the brain. Each of them has got several thousand connections coming into it. And the standard model will effectively, for every neuron at every time step, and you're going to want to do this 1,000 times a second, it's going to look at every one of its inputs and see how active it is, multiply that number, the input activation level, which is a floating point number, by another floating point number, which is the synaptic weight, and you do that for every neuron in the brain 1,000 times a second. Now, I reckon if you do that, you just add that up, you need 500 petaflops to do that. Now, a petaflop is 1,000 million. Is that right? No.
10 to the power of 15?
10 to the power of 15, whatever. Lots of zeros.
It's more than that, isn't it? I think an exaflop is 10 to the 18.
18.
And so 18, petaflop is beyond that, isn't it? No. 500 petaflops is half an exaflop. Oh, I beg your pardon.
We've now got exaflop computing. It's just arrived. But we're talking about machines which are incredibly power hungry. And so, for instance, running a simulation in this way of the human brain would take the world's fastest supercomputer to do it in real time, and it would use 30 megawatts of power, whereas the human brain, everybody knows, only uses 20 watts. It's less than a light bulb, basically. It's 1.5 million times more power efficient than doing what most people are considering. You could say, oh, that's okay. We can humans are cheaper. We don't have to pay those electricity bills for the 30 megawatts to run this thing, so we're okay. Unfortunately, that argument doesn't wash because, firstly, there are lots of people working on sort of low power systems, chips from Intel and IBM and companies like BrainChip and others who are making very low power chips, particularly for edge computing. If you're processing sensory data, you can do that with a tiny chip that's using a fraction of a watt, and so you can do quite a lot of stuff. You won't be able to do the whole brain, though, that way, because, well, even the best of these low-power neuromorphic chips will only do about 1 million neurons on a chip. So to do 86 billion, you'd need 86,000 of them, and that's not really reasonable.
And Simon, is the central difference between what a human brain does and what a machine does that the machine has to activate every single neuron in its system to do a single calculation, to do a single process, whereas the human brain only uses a small number of the neurons in a brain for each process?
Essentially, that's it. Yeah. So the standard way of doing neural networks effectively doesn't matter whether the system's processing any information or not. You have to take for every neuron. You have to look at all of its inputs to see what they're doing. Now, in the real world, in the real brain, basically it's event driven. There's quite a lot of people who've been interested in this. So rather than processing all the time, an event comes in and you process it. And in neural terms, this is what real neurons do. They don't send floating point numbers around. They send spikes, the pulses. So the retina, for instance, if you flash an image on the retina, you've got a million fibers coming out of the back, and you will get a wave of spikes going through, which can be very sparse, actually, with a very small number of neurons that actually have to fire. And you can simulate this much, much more efficiently. So because you only do processing when there's something to do. And this goes back a long way. I've been pushing this idea for 30 years, essentially. And back in the 1990s, one of my students, Arnaud Delorme, developed a thing called SpikeNet, which was an event-driven spiking simulator. Amazingly, his code can still be downloaded today. It still runs. But back in the 1990s, we used it to process a complicated image with actually 400 different faces of 40 different people, 10 different views of each of them. And it would recognize every one of them and say, well, it got 99% correct. It did actually make a couple of errors, but it was identifying them and localizing them in the image. And it took 30 minutes in 1999.
So, Simon, forgive the stupid question. Why does a machine have to activate every neuron in its system to deal with each event where a brain doesn't? Why do you have to get everything going in a machine all the time? Why are sparse networks so unusual?
Well, you don't. So, yeah, a lot of people in neural computing and AI now are still, I think, wedded to the idea that you need to physically implement every synapse in the system and so on. So, we were listening to the people from RAIN computing, and they're bringing out chips that use memristors to replace the brain synapses. But if you want to do the entire brain, that's 100 trillion of them. That's a lot of hardware. But my claim is that actually you don't need any of this, because essentially if I want to simulate something the size of the brain, I just need to know which neurons are fired and to update their outputs. It actually turns the whole computation the other way around. So I would say 99.9% of all the people doing neural networks and AI now are working backwards. They say, I'm going to look at every neuron and look at all its inputs, whether those inputs are on or not. And that's incredibly expensive, and that's why it takes 30 megawatts.
Let me just interrupt you, because that seems such an obvious inefficiency to go through the condition of every single neuron in the system. Why are so few people working on sparse networks when it seems like such an obvious thing to do? It's not as if it's a well-kept secret that machines are energy intensive.
We'll be right back after a quick break.
The People in Performance podcast offers insights into the strategic competencies, behaviors, and results needed to increase the performance of employees and leaders. The show looks at all areas of the world of work, including attraction and recruitment, onboarding, training, and succession planning. Tune in to get a better handle on the stages of workforce planning you need to master in order to guarantee long-term success in a rapidly changing world of work. New episodes drop each week. Check out the latest People and Performance episodes on your podcast platform of choice. Follow us on socials and read the latest articles at pppod.com.
Yeah, quite frankly, I don't understand it either. I've been preaching this one for 30 years, and there are still people who say that the fact that neurons generate spikes is an irrelevancy. Just a few months ago, there was a really interesting debate where I'm going to forget the names. It was Jan LeCun was one of them, the head of AI at Facebook. There was the head of NVIDIA research, and both of those guys said, well, we know that neurons send spikes, but this is we don't care. We're going to do it all with floating point numbers. And so, for instance, I'm blocking on the name of the guy. This is terrible. But anyway, the head of NVIDIA, he said, if you want to send an 8-bit number with spikes, you have to send 255 spikes. No, I'm so sorry. If you want to send an 8-bit number, one spike is plenty. And in fact, there's a very simple illustration of this. How many bits of information can you send with one spike? Well, if you got a million fibers in the optic nerve, and you're lying on your back, looking up, looking at the sky. You've got your eyes closed. Then you open your eyes and you say, "Where's the brightest star in the sky?" You could look at the firing rates of the million fibers in your optic nerve, count them, and then sort them and find out which one was firing fastest. Or you could just say, which one fired first? It's been known since the very, very first studies on the visual system by Lord Edgar Adrian in Cambridge in 1927. He got the Nobel Prize for this. That if you flash a light on the retina of an eel, actually, the latency, the time it takes to get the neuron to fire a spike, depends on the intensity. It was in the very first paper, and that's been ignored by everybody, basically, who said, oh, yeah, the neuron fires lots of spikes, we can count how many, the firing rate. And that's when people like the guy from NVIDIA and Jan LeCun say, spikes are irrelevant because we can do it all with floating point numbers and it works fine. They're missing this point that biology does it on incredibly low power because you just need one spike. And let's just remind ourselves, you've got a million fibers, you get one neuron to fire one spike, it's the brightest star in the sky. How many bits have you got? Well, it's how many? A million is 2 to the 20, is it? Something like that. You've just got 20 bits with one spike. That's how powerful a spike is. If you know it's the first to fire, and that's the trick.
A couple of quick questions. Isn't it the case that many of the chips have moved away from floating point to simpler arithmetic, fixed point? I thought that was one of the innovations that Google made in their TPUs rather than the GPUs they'd inherited the ideas from. And so that simplifies some of the processing.
Yeah, NVIDIA, if you take their latest architectures, they actually offer, you can do things in 32-bit floating point, 16-bit floating point, fixed point things. You can get down to 4-bit, 2-bit, and even 1-bit, which is actually sounds pretty close to spikes, except there's no timing in it. So if you've got an NVIDIA architecture and you're processing, you've got a 10-layer network like AlexNet, and you're doing it with this sort of architecture, because of the way they do it, it doesn't matter whether you're only using 1 bit per synapse. It has to do everything has to be done. There is no interesting dynamics. You don't get the fact that the brightest point in the image is processed first. You process the entire image, and so you make some savings. You get the NVIDIA chip, if you're running at low resolution, will be more power efficient. You can increase the power efficiency by a factor of, let's say, 1,000 by chopping that down. But
you said that 99%. You said that 99% of the AI is working on this dense or widespread systems, and very few are looking at the sparse systems. We had Alexa Gordich of DeepMind on episode 6, and he did sing some praises of what he called sparse systems. He referred to something called MOE, and I think that's mixture of experts. Is that a phrase that you've come across? Are there other people apart from yourself pursuing this idea seriously?
Well, certainly, I think one of the nice things about using spikes is that they're like symbols. One of the big problems with standard, deep learning trained networks, you end up with this thing, and it gets the right answer, and it can tell you what breed of dog it is and all the rest of it. But trying to work out what the reasoning was is impossible, because it's all basically huge numbers of floating point multiplications and so on. If you can sparsify the data, you can get it down to a level where you can actually understand what's going on. Now, this is actually a rather unpopular idea in neuroscience. I've been a proponent of the dreaded grandmother cell theory of how neurons code things. I think we have neurons. I mean, actually, I recorded one when I was doing my thesis. It was a banana cell. It was in the bit of the frontal cortex of a monkey, and it responded to a banana whether the monkey saw it or whether he tasted it. It was a bimodal concept cell. Now, in humans, there's lots of data now showing you have concept cells for Jennifer Aniston and Darth Vader and things like this. And these are neurons which will respond to any photograph of the person, or their name written down, or somebody saying their name, or probably, it's not been tested, but if you just heard their voice, if you heard, that would also activate these neurons. These are symbols. And
Simon, they're called grandmother cells, presumably because people have a cell that responds to their grandmother.
Well, this was actually it was an insult, because back in the 60s we knew that chicks would imprint on their mothers. Right, so the chick born from the egg, and you got Konrad Lorenz wandering around with his yellow boots on, and the chick will imprint on the yellow boots and treat it to be its mother. And so the idea that you'd have neurons that would become selective to mothers was already reasonable, but then to basically dismiss the idea that you could extend this, he said, well, you might as well have a neuron for your grandmother. And so the grandmother cell hypothesis was supposed to be a way of ridiculing the whole concept. But actually, I think that and Horace Barlow, by the way, who's one of my favourite researchers, was arguing from the early 70s that we needed neurons that had the coding power of symbols, words, and things like this, would have neurons that were specific to that. And once you allow that, then you can have a super sparse system in which the neurons correspond to concepts, and you can do what actually people were doing back in the 60s. It's a semantic web. Imagine a sort of huge network with a billion things corresponding to different concepts, and then you say something like you're playing University Challenge, and Jeremy Paxman says which composer born in 1756, buzz, whatever, Mozart. You had three things: composer born 1756, and that's allowed you to access Mozart.
Is that an expert system?
It is. And so an expert system and a neural network with spiking neurons is effectively the same thing. And so the super low power that you get from the human brain is because it's like a sort of symbolic expert system where the neurons are symbols and spikes are when they're instantiated. And that gets your power down by a factor of 1 million.
So Simon, this sounds very exciting in theory. Can you point to any experimental progress that you or other teams have made in the last few years as to verifying that these ideas could be turned into silicon?
Well, I don't. For a long time, I've been interested in actually generating, dedicated silicon. So, I had a company called SparkNet Technology, which was acquired by BrainChip Incorporated in 2016, and BrainChip make hardware chips. I mean, it's a Akida chip, as I say, it's good for doing edge computing and things like this. Probably not so good for doing really large scale stuff. But since then, I've actually been looking at. I call it the terabrain project. It's the idea that I think we can simulate neural systems as big as or larger than the human brain on standard off-the-shelf hardware. And to prove it, last year we had a student. He was Pierre Kukel. He was doing a master's thing, and he was using an NVIDIA top-of-the-range GPU, and he simulated a network with 1 billion neurons, 100 million inputs, only binary connections, but lots of them, about 40 billion connections, I think, and then 4 billion connections, beg your pardon, and then you take a packet of 1 million spikes in the input and you propagate them into the system, and it takes 18 milliseconds on this GPU. That equates to 2 billion updates a second. This is just using standard, architecture with, it's got all this floating point hardware in it, which is totally irrelevant because actually all the neurons are doing is counting events. We've done the same thing with my another master's student who just finished his master's, Aditya Kar, who's going to start a thesis with me very shortly, and he's doing it on a Mac. So he's been doing it all on a Mac, a MacBook Pro. It's got the M1 chip from Apple, which has got 16 gigabytes of memory on the chip, and it's very fast. You also find these in iPads, by the way. You can buy yourself an iPad. It's got an M1 chip in it, and we've done 1 billion neurons with 100 billion connections coming in, and okay, it's probably 10 times slower than the GPU, but it's using 39 watts. And the other thing is we've got our homegrown learning rule using only binary weights. We're basically learning to recognize things that repeat. Is basically a question of moving the weights around so they match the thing coming in. And one of the things that humans do, which is incredibly impressive, is that we spot things that repeat incredibly easily. So if you just take meaningless noise, if you recorded that and then you played it as a loop, within a few repeats, you can hear that it's periodic. I mean, it doesn't matter what it is. It's called frozen noise, discovered in 1963. We did some experiments a few years ago which showed it was a true memory, because basically you train yourself up on this sound you heard, you go away for 3 weeks and you come back in, and the first time you hear it, you recognize it. It's meaningless, but you spotted it. And this is what humans do really well.
With your terabrain, Simon, if you're simulating 1 billion neurons with one M1 chip, I don't suppose you can just buy 86 of them and then, hey presto, you've got a human brain because you've got 86 billion neurons.
I don't even need 86 max. I haven't actually bought it yet, but the M1, the Mac Studio Ultra, uses the M1 Ultra chip, which has got 128 gigabytes of memory on chip. Now, my claim is that 1 byte per neuron is plenty, because basically you're just counting up to maximum 255. Actually, you don't even need that, because basically to say composer born 1756, that's 3 things that you have to hit. It's not and the Mozart neuron is counting. And it can feed together all these things, and it doesn't need that. So basically, I think on the Mac Ultra I could do the entire human brain.
So as we're coming towards the end of our time, let's look at the future. What are you expecting will be the impact of your ideas anytime soon? Will it address the paradox Callum mentioned at the beginning, that although there's lots of ideas about AI, it hasn't actually been adopted very significantly by many companies yet?
Well, I think my guess is that if people, by the way, I'm no longer in the business of trying to sell all this stuff. When we get this done, we're just going to dump it, so anybody, the code It's just standard code. You can get it, if we can get the thing to run on a Mac or whatever, we'll just give it away, and so people will be able to use that technology to do whatever. One of the things I think will be very important is that you would have local learning. So you could have the next year's phone running this sort of software would be able to learn about everything that you do, which is repeating, but you don't have to tell Google and Facebook about it. So your phone would be learning things about what you're interested in without you having to Google everything and your personal information being sent to Google so that they effectively know everything about you. I think people are going to find that extremely important. Yes, you will download every now and then the entire contents of Wikipedia and things like this, so that your phone is up to date. But I mean, the storing all this data is not a problem anymore. Remember, GPT-3, this thing, which writes, articles for The Guardian 2 years ago, which, are you scared yet human? It has 175 billion parameters. That might sound a lot, but it's 175, if you're using, let's say 32-bit things, I mean, it's 4 bytes per parameter. We haven't even used a terabyte yet. And my phone can have a terabyte of memory. So you could probably get everything to do GPT-3 on a phone. Of course, OpenAI don't want to do that yet because they got everybody logging in and playing with it. But frankly, I mean, you could get all of that running on an iPhone, I think.
So when is this likely to happen? Is it
next year?
In a year or two's time?
Yeah.
Next year?
Yeah, for sure. I think.
Maybe we'll bring you back next year and discuss what's happening next.
Or maybe we'll bring your bring your terabyte back and have a conversation with it instead.
Yeah, exactly. I was thinking, this joke that your phone knows more about you than than your wife does, because whatever. I mean, you've got all that stuff on your phone, and yes, the day I pop off, I would. There would be a lot of stuff about me, and you could run a simulation of me and ask me questions, and I wasn't there anymore.
I look forward to that, Simon.
Karen's written books about this, right?
Simon, thank you very much for joining us. Fascinating exploration of sparse networks.
Yeah, sparse networks does sound like a subject that deserves more attention.
Agreed.
Thank you very much.
It's been a pleasure.
And for people listening, we'll listen out for more episodes, usually once every week, usually available on Wednesday mornings.